I'd like to take questions from you, but I'll wait for few minutes. If anyone joins, then it would be better to take questions, or else I will just solve few questions and then I will wrap it up, and we'll see show you few MATLAB commands. And okay, so I'll just wait for a few minutes. So, as no one still did not attend the uh, this extra session class yet. So I'm just solve few questions from week 1 to week 8, and I will show you a few commands of MATLAB, how to use that. A very simple command you already knew. Uh, so let's start. Let's share my screen first. So I'll start with, since I'm not going to discuss discuss anything detailed about anything, because you already knew how this is done. So I'll start with the questions. The first questions is like, so the question is given to you is like, which of the following statement is true? I'm just reading out the questions, and I'll give you the answer. So the question is, which of the following statements are true? So in the diagonal canonical form, all the eigenvalues are different. In Jordan canonical form, some of the eigenvalues are the same. Both A and B. This is option number C. The first option number 1 is in the diagonal canonical form, all the eigenvalues are different. Option number 2 is in the Jordan canonical form, some eigenvalues are same. Option number 3 is both option 1 and 2 correct. And option number 4 is in Jordan canonical form, all the eigenvalues must be same. So the correct answer, as you know, because we know that in diagonal canonical form, all the eigenvalues lies in the diagonal, right? But in the Jordan canonical form, you see, so in diagonal canonical form, the format is something like that. I'm not giving the whole detail about all this. The A matrix is look like something. Let's say lambda 1, lambda 2, up to lambda n. So there are all zeros over there. So this is the diagonal canonical form. And Jordan canonical form is something. So A matrix is looks like, so you will get some sort of a Jordan block. Like you will get lambda 1, there is a 1. Then you might get lambda 2, there is a 1. So if we increase the length of the matrix, something like this, so there may be possible that you will get 1 lambda 3, then lambda 4, 1. So that means these all elements are zeros. These are, so this is one Jordan block. This is one Jordan block. This is another Jordan block. This is another Jordan block. And this is another Jordan block. And other elements are zeros. So definitely, so you can see that in diagonal canonical form, all the eigenvalues should be different. If there are few eigenvalues are same, that means that the form is not diagonal anymore. Because you can see there is a one, the number 1, the element appears in the off diagonal form. So it is not a complete diagonal one. So option C is correct. That is, in diagonal canonical form, all the eigenvalues are different. In Jordan canonical form, all the eigenvalues are same. Okay. Next questions asked. You are given a transfer function. So you are given this transfer function s square plus 3s plus 2 and asked to obtain the state space solution, right? Not solution, sorry, state space representation in diagonal canonical form. So this is your question. The question is very easy. I mean, So first, what we do first we need to find out the eigenvalues by solving this characteristic equation. So this is a square plus 3s plus 2 equals to 0, and the root of these are -1, -2, right? So the eigenvalues are -1 and -2. Okay. Then what we do? So this is, you see that here there is a 0 in the numerator. So in that case, what we do the, so this is a square plus 3s plus 2. So we use the separation principle by, let's say, C1 is equal to S plus 1 plus C2 is equal to S plus 2, and we need to find out the C1 and C2. So when we equate this equation, these two equations, so what we get, 2s plus 5 is equals to C1 into S plus 2 plus C2 into S plus 1. So solving this equation, we get C1 equals to 3 and C2 equals to -1. Okay. So this is your GS, that is 3 by S plus 1 plus -1 by S plus 2. This is your GS. So which is basically, GS is basically YS by US, right? Now multiply US both side, we'll get 3 by S plus 1 US plus -1 by S plus 2 US, right? Just a minute, I'm just check one thing. I think some mistake is over there. So what is your, so we choose this portion as a x1s and this portion as a x2s. As you can see from here, we choose this portion as x1s, this portion as x2s. So just a minute, I'm just trying to figure out something. So what is x1s equals to us divided by s plus 1, then cross multiplication, x1s is equal to minus of x1s plus us, and here you do us by s plus 2, and that is s x2s equals to minus 2x2s plus us. So what you get, take a inverse Laplace transform, x1 dot equals to minus x1 plus u, and x2 dot equals to minus 2x2 plus u. Okay, so what you get, x1 dot x2 dot equals to -1 0 0 -2 x1 x2 plus 1 1 u, and from here, so what you get is ys equals to 3 x1s plus minus x2s minus 1 x2s, right? Take an inverse Laplace transform. So y of t equals to 3x1 of t plus of minus x2 of t. So therefore, the output equation y is equal to 3 minus 1 x1 x2. Right? So this is the diagonal form. So I hope I'm not going to give a full detail of I'm not going to do any kind of any example regarding this. So this is the sort of you can find out the diagonal form, diagonal canonical form using this method. Okay. So now I'm going to move. I move to the next part is stability part, because there were few questions regarding regarding this Lyapunov stability. Okay, so they students basically ask like how to find out the Lyapunov function, system is stable or not. So I'm just going to give us small details. Then I'm going to I will discuss about all those things. Okay, so Lyapunov stability. So what Lyapunov stability says? So first of all, it is this Lyapunov function, as we all know, a, basically mathematician Lyapunov used a function to determine the stability of the system. Whether the system is a linear system or non-linear system, doesn't matter. We can find out the stability of the system using this method. So what the logic of logic behind this, how to find out the stability? So the logic says that you have to choose a function v. So let's say I choose a function v. So v is said to be a candidate Lyapunov function. Why I am calling it as a candidate Lyapunov function? Candidate Lyapunov function because we don't know using this Lyapunov function we can guarantee the stability or not, because we will see that there are few Lyapunov function which satisfy all the characteristics which is needed to be, but still that function is failed to satisfy the stability of particular system. So that's why we call it a candidate Lyapunov function. Okay, V is said to be a candidate Lyapunov function if V is continuously differentiable, positive, definite function. That means V should be continuous, V should be differentiable, like we can take the derivative of V, we can, and V is not a discontinuous function, it's a continuous function. So we can't choose any modulus function, something like mod x, because at mod x is not differentiable at point 0, right? So you have to choose something in such a way so that function should be continuously differentiable and positive definite function. So what is positive definite function? Positive definite function is said that, let's say v of x is, v of x means v is a function of x is always greater than 0 for any x, x के कोई the for any value of x, that vx should be a positive function. It will give a positive result, and vx equals to 0 if and only if x equals to 0. If these two things satisfy, that means it's a positive definite function, right? So these two things you need to come up with. Whenever you find a Lyapunov function, first you have to think that that function should be a continuous, it should be a differentiable, it should be positive definite. These three things has to be satisfied. Then we can say this is a candidate Lyapunov function. And if we take the derivative, and if we take the derivative of Vx with respect to time, that is v dot x, then if v dot x is less than or equal to 0, implies, that means v dot x is less than or equals to 0, that means v dot x is negative semi-definite, which implies system is stable in the sense of Lyapunov. Two, if v dot x is less than 0, strictly less than 0, that means negative definite implies asymptotic stability. Okay. And 3, if v dot x equal to 0, okay, the value of v dot x, that means implies the marginal stability. Okay. So now there is a there was one student who asked the question because during class that he was not able to understand how they choose this function. So the function is given to you is x1 dot equals to x2 and x2 dot equals to minus x2 minus x1 cube. Okay, so this is the function that you are given, and it says that find out the stability of the system. So now, since you know the how to find out the stability using Lyapunov function, because it is very easy for linear system. Let's say I have a system like x dot equals to ax plus bu, or x dot equals to ax, like this. Since this nonlinear equation is a autonomous equation, or you say there is a no external control input u over here, right? So in case of linear system, if the system is x dot equals to, let's say, x dot equals to ax, so we can say the system stability by checking the eigenvalues of A. If the eigenvalues of A lies in the left half of the complex plane, then we say the system is stable. If it is not, then we say system is not stable. Or if it is lie in the imaginary axis, then we say system is marginally stable. So it is very easy for linear system, but it is quite difficult for non-linear system because it is difficult to find out the eigenvalue, right? We cannot put it, we cannot form this equation into a x dot equals to ax plus bu format or x dot equals to ax format. So it is very difficult to find out the eigenvalue. So there is a stability proof, that is the Lyapunov stability. So first, let's say I choose a Lyapunov function v of x equals to half x1 square plus half x2 square. So I choose x1 square and x2 square because there are two states only, x1 and x2. If there exists a third state, so I have to choose I have to use a third state in the Lyapunov function as well. Okay. So this is my first Lyapunov function. So I call it, sorry. So I call it a candidate Lyapunov function. Okay. Now take a derivative. Okay. So what we get, v dot of x equals to x1 x1 dot plus x2 dot, right? Now put the value of x1 dot and x2 dot. What you will get, x1 x2 dot x1 dot equals to x2 plus x2, and x2 dot equals to minus x2 minus x1 cube, right? So what you will get, it is x1 x2 minus x2 square minus x1 cube x2. So it is very difficult to say whether this system v dot x is negative definite or not, or negative, at least negative semi-definite or not, because you don't know about this, you don't know about this term, you don't know about this term. You know that this x2 square is always be positive, whether the value of x2 is negative or positive, this x2 square gives a positive result, and because of this minus, the minus x2 square gives a negative result. But you don't know whether this term x1 x2 will give you a positive result, or this x1 cube x2 give you a positive result or not. You don't know, right? So in that case, that means this is undefined. This is, this case is basically undefined. That means we cannot conclude anything, that whether the v dot x is a negative semi-definite, whether the v dot x is less than 0 or less than equals to 0 or equals to 0. We cannot say anything, right? Because this should be done for any value of x. This should be v dot x less than equals to 0. This should be done for any value of x, whether it's a positive or negative, for any real value of x. Similarly, this v dot x is less than 0. This should happen for any value of x, real x. And similarly, this third one. So we cannot say anything. This that means this function is not a function by which we can find out the stability. Okay. So let's move to the next function. Okay. So I choose v of x equals to 1/4 x1 to the power 4 plus half x2 square. I can choose that because x1 is positive, this term is positive, this term is positive, both are continuous, both are differentiable. Whatever value of x1 and x2 you will choose, you will get a positive value, and this v of x will give you a 0 when x1 and x2 both are 0. Okay. That means this could be a candidate Lyapunov function. Now we will see whether using this function, can we comment on the stability or not. So let's take a derivative. What we'll get, it's x1 cube x1 dot plus x2 dot. Okay. So x1 cube x1 dot, what is x1 dot? It is x2 plus x2 into what is x2 dot minus x2 minus x1 cube, right? So what you will get, it is x1 cube x2 minus x2 square minus x1 cube x2. These two terms cancel out. So what you will get, this is x2 square. So at least we can say the system is negative semi-definite. Why I say this is a negative semi-definite? Because for any value
let's say x1 is positive or negative, doesn't matter, or 0. For x2 positive negative, it will give a negative result. Okay. If x1 0 and x2 0, it will give you a 0 result. If x1 something, any non-zero value, and x2 0, this is also gives a 0 result. That means the system is, so this is not negative definite, this is negative semi-definite, because definiteness, we conclude, we say that something definiteness means when it is happen if both the x's value is 0. In case of positive definite, we say that v of x is 0 when x is 0. That means, or v of x, here x is basically x1 and x2. So when the x1 and x2 both value is 0, then it should be 0. But in that case, if you choose x1 equals to, let's say, 1 and x2 equals to 0, still this gives you a 0 value. That means this is not a definite, this is semi-definite. So that's it. That's why I say this is a less than or equals to 0. So at least I can comment on the stability. The system is stable in the sense of Lyapunov, right? System is stable in the sense of Lyapunov. Now, whether the system is asymptotically stable or not, we cannot comment on that. We cannot comment on this using this Lyapunov function. In I mean, there's a advanced studies. There are different theorems exist. There exist different theorems like Lassel's theorem. Using that, we can comment on the stability of the system. But since those are not included in your curriculum, so I will not talk about that. So basically, using this function, using this Lyapunov function, you only comment on the negative semi-definiteness of the v dot. Now I will choose another function. I will show you that, okay, using this function, we can guarantee the asymptotic stability. Okay, that's that function. I think this question has been asked in your assignment as well. And since you all get the assignment answer, so you see that they use some function, v function, which looks like it's not a positive definite, but it's a positive definite. I'll show you. So the next function that is chosen, it's x1 to the power 4 plus x1 square plus 2x1 x2 plus 2x2 square. So it does look like, okay, this term is positive, this term is positive, this term is also positive. Whatever the value of x1 and x2, this three term is always give a positive result, but this term does not gives a positive result, right? It does look like that, because if x1 positive, x2 negative, this term will give you a negative result. Or if x1 negative, x2 positive, this will give you a negative result. So this will only give a positive result when x1, x2 both positive or both negative, right? Only this term. But I'll show you that this is also a positive definite function. Why? Because we can restructure this function in that format, right? So this is also a positive function. You can see that whatever the value of x1, x2 you choose, whatever the value of x1, x2 you choose, you will always get a positive result. You will never get a negative result. But the one problem with this, one problem with this approach is that this is not definite. Uh, this does not gives you a definiteness, because as you see, what positive definite function says, the v of x is greater than 0. Let me see. No, it will give you a definiteness. Sorry, as my mistake, it will give you a definite. So this is the positive definite function, because whatever the value of x1 and x2, let's say I am choosing x1, x2 are similar but opposite polarity value, still you will get a positive result. Whatever the value of x1 and x2 you choose, you will get a positive result, and you will get a negative result if and only if the x1 and x2 both are 0. So that means this is a positive definite function, right? So we can consider this as a candidate Lyapunov function. It satisfies all the qualities to be a candidate Lyapunov function, right? Now take a derivative. So v dot x equals to 4 x1 cube plus 2 x1 plus x2 into x1 dot plus x2 dot plus 2 x2 into x2 dot. Sorry, I forgot to mention x1 dot over here. So it's 4 x1 cube, x1 dot is x2 plus 2 x1 plus x2, here x2 minus x2 minus x1 cube plus 2 x2 minus x2 minus x1 cube. Okay, so what you will get, 4 x1 cube x2 plus this x2 and x2 cancel out. Yes, so 2 x1 to the power 4. I'm sorry, it's 2 x1 plus x2 minus x1 cube minus 2 x2 square minus 2 x1 cube x2. So this is 4 x1 cube x2 plus, sorry, not plus, it's minus 2 x1 to the power 4 minus 2 x1 cube x2, 2 x2 square minus 2 x1 cube x2. So this three term cancel out. So what you will get? You will get 2 x1 to the power 4 minus 2 x2 square. So this is your v dot x. So this is for sure is a negative definite function, because this will give for any value of x1 and x2, this will give you a negative result, and it will give you a 0 result only when x1 and x2 both are 0. That means this will give you a negative definiteness. So that means system is asymptotically stable. So basically, what did we learn from this? We learned from this, like the Lyapunov function for a particular system is not a unique one, right? So you will find that few Lyapunov function does not work out for this system. If a Lyapunov function does not work out for this system to find out the stability, that does not imply that your system is unstable. Okay, that does not imply. It will give basically you have to keep on checking that what Lyapunov function will actually work on that. So that's why it is called as sufficient condition, not a necessary condition for nonlinear system. So you see that this first Lyapunov function does not work out to find out the stability. The second Lyapunov function does work out for the to find out the stability, but it does not establish or it does not guarantee any asymptotic stability of the system. Okay, so it only says that system is stable. Okay, but the third Lyapunov function gives you a complete notion of asymptotic stability. So that means this is not a unique one. You have to keep on checking. So there is no particular way to particular procedure to find out that there is no particular procedure to find out the Lyapunov function. You have to keep on checking, and you have to check that whether this will work or not, or whether that will work or not. So this is sort of a rigorous process, but in general, uh, you will definitely accustomed with how to find out this whole thing. But if your system is a linear system, then this Lyapunov function will always give you the necessary and sufficient condition. Okay. For nonlinear system, it will only give you the sufficient condition, not the necessary condition. So similarly, so there is a question I mean, there is a question from matrix theory as well. I mean, you all know, but still I find I'd like to discuss these things to all of you. The question says that there are the three statements given to you, and among them, which are basically true, you have to say. So the first question says that if a matrix A is a symmetric one, then the eigenvalues of A can be real and complex conjugate. Okay. So we all know that if your system is a symmetric, if your matrix is a symmetric matrix, we always get a real eigenvalue. So that means first is not correct because here already include the complex conjugate. The trace of a matrix A is equal to the sum of the eigenvalues of the matrix. Definitely, the trace of a matrix is basically the how to find out the trace of a matrix. We just need to add the diagonal element, right? We basically add the diagonal element, and that is basically equal to the sum of the eigenvalues. And the multiplication of eigenvalues gives you the determinant. Okay, that's why if your system is a singular, or if your matrix is a singular, means if your determinant is 0, this signifies that at least one of the eigenvalues is 0, because when you multiply the eigenvalues, if there is a one eigenvalue that is 0, so obviously this multiplication will be 0. And the third statement is if a matrix is symmetric, then its eigenvalue is always 0. So this is true, that I have already said you before. So which of the following, next is very nice question. So which of the following statement is true? So the statements are the Lyapunov stability criterion can be used for linear time invariant system. Lyapunov stability criterion can be used for nonlinear system. Then both A and B are true and none of the above. So Lyapunov stability can be used for a definitely nonlinear system. Definitely, it is basically designed. It is basically generated to find out the stability, find out the notion of the stability for nonlinear system. That is the main notion to find out the main notion of generation of this Lyapunov stability. And definitely it can be used on linear time invariant, linear time varying system, time invariant system. Both cases we can use. But since you are not studying the time varying system, you are basically studying the time invariant system. So this is not need to, you are not need to basically worry about all those things. So now I'm going to show some, since I don't know what are basically you are since no one attend this class, so I don't know what question I should take and what are the doubts I should cover. But okay, so I'm not yeah, topic this. I'm just showing you few MATLAB few. It's not few. I'm show you MATLAB code, something related to decide how to use this MATLAB code. I hope you all are able to sign in a MATLAB, online MATLAB, are all able to sign in online MATLAB. So just so I just stop this presentation and start I share my screen over here. So I hope you're all able to see my screen, right? So this is online MATLAB. So here you can so what you can do is just a minute. So first thing is, let's say you have a system. What is the command for transfer function? You know that what is the command for transfer function, right? Yeah. So let's say this is numerator. Numerator is basically 2 and 5 that I'm giving. Okay. And yeah. And this is denominator that I'm giving 1, 3, 2. Okay. So, so the system transfer function is basically you have to use the TF. So TF is basically TF signifies the transfer function, and you have to provide num, sorry, num comma 10. Okay. And this is your, so basically this is your transfer function, right? You get the transfer function. So now what to use from to transfer function to uh, state space? So there is a command called TF to SS and SS to TF, right? So there is a command TF to SS. So let's say second system, I'm just using this TF to SS num and den. So this is basically giving you, oh, I think I did something wrong. Yeah. So TF to SS, you have to provide A, B, C, D, and then so this is basically TF to SS. So you have to, I did a mistake over here. I just put only sys underscore 2, which basically that's why it gives only A matrix. Okay. So you have to give A, B, C, D, all 4. So this is your A matrix, this is your B matrix, this is your C matrix, and this is your D matrix. Okay. And then SS to TF, that means we have a transfer state space form and we need to transfer it into a transfer function form. So in that case, what should you do? It will give you, you have to give, let's say, numerator and denominator SS to TF. Okay. So let's say first you make this ABCD into a state space format. I'm just transforming this ABCD transform, what ABCD that I get from this, I'm just transforming this into a transfer function again. Okay. So here you just need to let's call it a system state 2, system 2, and this is SS. SS is a state space. So you just give A, B, C, D, and your this is your system. So your system now become combined in a state space format. Okay. Now you have to use transfer function SS to TF. Okay. So for that case, what you want numerator and denominator. And what command you should use? You should use SS to TF, right? SS to TF, and you give system 2. Yeah. Okay. Did I do something wrong? Okay, you have to give ABCD whole. So you do not need to do that. You have to give ABCD whole. So as you see, the numerator is 2, 5. That means 2s plus 5. And the denominator is 1, 3, 2. These are only coefficient. That means s square plus 3s plus 2. So this is whole about your transfer function to state space to transfer function model, and how to find transfer function using TF command and state space using SS command. Okay. Now let's say you have a matrix called, let's say A is a matrix. I'm just write down the matrix. Let me get a matrix from here. That will be better. Yeah. 2 minus 1 1 minus 1 2 minus 1 and 1 minus 1 2. So this is my matrix. Okay. Now you need to find out the eigenvalues, and you can also find out the eigenvectors as well. So what should you do? Let's say I am using d comma v. Okay, is equals to, you have to use the command eig, that is basically I of a, and you will get this. So this v is basically matrix, diagonal matrix, where the diagonal elements are the eigenvalue. This V matrix is basically gives you the diagonal matrix where the diagonal elements are eigenvalues. Okay. And D matrix is basically the eigenvector matrix, where the first column, that is 0.0182, then 0.7160, and then 0.6978. This is the eigenvector corresponding to eigenvalue 1. Then the next one is the eigenvector corresponding to eigenvalue another 1. And the third one is the eigenvector corresponding to 4. So if, let's say, if you use only uh, let's say E equals to EIG, I'm not using D comma V, I'm just using a single variable. E is equal to U. This will give you the only the eigenvalues. This is the 1, 1 and 4. And when you do this kind of structure, when you give MATLAB this kind of structure, it will give you a eigenvector and the corresponding eigenvalues. Okay. So this is the beauty of MATLAB command. Okay. And you know that you need to find out the determinant. If you want to find out the determinant of a matrix, you just use the command, let's say H is equals to determinant of det of A. You will get the answer. The determinant of A is 4, and you will get it from here, if you, because I have said already that determinant is basically the multiplication of eigenvalues, that is 4 into 1 into 1, which will give you 4. So the determinant is 4. Okay. So for that determinant you use det command. Okay. And now you need to find out the, let's say, controllability and observability. Okay. So you are given a matrix. Let's say I'm using another matrix. A equals to 0, 6, minus 5, 1, 0, 2, and 3, 2, 4. This is your matrix A. Okay, this is your matrix A, and B matrix is 0, 1, 2. Okay. Now you are asked to find out that the your system is, you're given a system. Let's say x dot equals to x plus b and y is equal to cx. This is a system. I'm just put here only A and B matrix. So you are asked basically to find out whether the system is controllable or not. So what is the controllability? Or for controllability, what you need to check, you have to find out the controllability matrix, that is B, AB, A square B, A cube B, this. So in that case, in this format, you can see that A is a square matrix, A always be a square matrix, that's for sure. And B has only one column. That means this is a single input system. Okay. So definitely the controllability matrix that you will get is it will be a square matrix. It will never be a um, rectangular matrix. Why it will never be a rectangular matrix? Because it is controllability matrix consists of B, AB, A square B, A cube B, up to A to the power n minus 1 into B. So this n is a size of the A matrix defined. So for 3 cross 3, what will be the size of the controllability? What will be the controllability matrix? It will be B, AB, and A square B. So B is one column. Multiplied A with B, it will give you another column, and multiplied A square with B, you will give a another column. So you will get a 3 column stacked together. So that's why it is a square matrix. So let's say C, not QC equals to CTRB. This is the controllability matrix command, and you have to put A comma B. So this is the controllability matrix that you get. First one is B, second one is AB, third one is A square B. Now you get this is the controllability matrix, but you need to find out the answer whether the controllability matrix is a full rank matrix or not. If it's a full rank, then we will say that okay, system is controllable. If it's not full rank, the system is not controllable. So there are two ways to find out the rank to find out whether this QC is a full rank or not. The first way is, since it is a square matrix, we can find out the determinant. So let's say I'm finding out the determinant. Let's say dt is equal to determinant of QC, and you will get a non-zero value. That means the system is full rank. You can guarantee. But there are another approach by which you can check whether the system is full rank or not, and that approach is much more appropriate approach, because in that case you do not need to find out the determinant, because if your matrix is rectangular matrix, you can't find out the determinant. So that's why the next approach is rank. So there is a rank command, rank, rank, and you put the matrix QC, you will get that the rank is 3. That means the QC matrix is a full rank matrix. Okay, so there's a true command. And another thing is, let's say I'm using the same A matrix, and here I give you the C matrix, which is 1, 2, and 3, because I need to find out the observability of that matrix. To find out the observability of that matrix, what command you should use? You should use OBSV. Okay, comma C, and you will get same an observability matrix. First row is C, second row is CA, and third row second row is AC, and third row is sorry, CA, and third row is CA square. Okay, and now you need to find out the rank of a matrix, and you will get the rank is 3. That means the system is a fully observable. Okay, so there is a OVSB. So you get to know the all the you get to know all the commands that you can use. The first one is the TF, by which you can find out the transfer function. Second one is TF to SS, transfer function to state space model. How to find out the state space model? You get the answer, you get the ABCD matrix, and then you say if you have a ABCD format and you need to combine all this ABCD matrix into a system, you have to use only the SS function, SS command, where you get on complete system. This system consists, so basically if I show to you, this is system 2. So this is basically, you see that this is basically a class file. You can see this is basically a class file where the A matrix, B matrix, C matrix, D matrix, and other things already inside over here. So this is basically a class file. So you basically generate a some sort of a class file where you put all these matrix. So once you call this is this underscore 2, you will get the all the value of that. So let's say particularly let's say you want only the A value, only the A matrix which is inside this underscore 2. So 2. So how you call? Let's say I call it AD and I want to call this underscore 2, and you need only the A matrix. So you have to use dot A and you will get the A matrix. So if you need BD and you want the only B matrix, so you have to do the dot B. Okay, so in that way, from a class file, you can get the you can fetch the values, fetch the matrices, whatever you need. So now the next thing I'm going to show you, because last class yesterday last class I have we have basically discussed about control sorry, state feedback control and state observer. We have discussed all those things, right? State feedback control, state observer, all those things, and we have seen that we have done some numerical examples, but in MATLAB there are few things. Let me. So first, let's say I have a matrix, a 2 cross 2 matrix, which is 0.5, 1, 1, and 2. This is my A matrix. Okay. And my B matrix is, let's say, single input system. I'm using single input system. Okay. 1 and 1. This is my B matrix. And I need that I want to design a control parameter, a controller gain K, state feedback control gain K, such that the closed loop system pole reaches closed loop system pole should lie in this region. What is the region? The region is what are the poles value? That is -1 plus I and -1 minus I. So I want, because this is a 2 cross 2 matrix, I want that the two poles should lie over here in the complex plane, left half of the complex plane. Okay. So here you can use two method. One is place and another is Acker method. So first, I'm going to show you the place method. So place, you get this k value. Okay, and I'll show you the Acker method. You get this value. Okay. So now, as you see, this is a single input system. I'm not talking about right now output because I have not mentioned any C over here. So let's say, okay, if you say it's not an issue. This is a CISO system. That is single input, single output system. That means you have only one input over here, and that signifies that your B basically contains only one column. Okay. So in that case, we can use this place command as well as the Acker command. As you already seen in the previous class, in the last class, as you have seen that in Acker command, we basically use a inverse term. If you remember, the formula is E transpose C inverse alpha D of A. This kind of uh, uh, this is the formula. So C inverse, basically you need a controllability matrix and that inverse should exist, right? So that means the first condition is your system should be controllable. That means your C matrix should be full rank. Okay. And the second condition is you can use this Acker command when your system has only one input. You can't use it when your system has two input or more than two input, because in that case your B contains more than one columns, and therefore your controllability matrix will become a rectangular matrix, and we cannot find an inverse of any rectangular matrix, right? So that means Acker command only possible when your system is single input, single output system. And by using the duality principle, so what duality principle says, it says if your original system is controllable, it means its dual system is observable, or vice versa. Now, if we say if the dual system is controllable, that means my original system is observable. Okay. So I use the next system I'm going to use. And here, this is the multi-input system or two-input system. And you will see that this Acker command will not hold. This is my A matrix. Okay. And this is my B matrix. Okay. Now I need my system pole should lie here. That's -2, then -1 plus I, and then -1 minus I. Okay. Now K, first I use the Acker command. So do I get the result? Let's see whether we get the result, because this is a multi-input system. According to the logic, we should not get any result. But let's see whether we should get the result or not. Obviously, we get a warning that error using Acker, because system must be single input. You can see the system must be single input. If the system is not a single input system, we cannot use Acker command. Okay. Now use the place command. Using the place command, you get the result. You get a result that is a k value, that is -2 0. This is -0 because the value of 0 is very less. You can see from here, you can consider it as a 0. this is not even giving you the further term, but you can see from here it is 5.5511 e minus 17. That means 10 to the power minus 17. So you can consider it as a 0. This is 1.5, this is 2, 1, and this is 0. So this is the k. So for multi-input case, you cannot use the ACAR command. You have to use the uh, place command. Okay. And also for single input case, wherever it is recommended that place command should use, ACAR command should not use. And in if you see if you do it in a there's another approach is a similarity transformation approach, right? So if you do the similarity transformation approach, you see you have already seen that in similarity transformation approach, we need to find a similarity matrix when we find out the feedback control. You have seen in the lectures in week 7, you have seen in week 7 that there is a one approach, that is you have given a desired pole location, you find out the characteristic equation using that pole location. Now you need to find out the k matrix or k vector. So you put u is equal to, let's say, kx, and you get that x dot equals to a plus bk into x, and you find the characteristic equation of this system. And these two, the desired characteristic equation and my characteristic and your characteristic equation, you just compare these two, and from here you find out the k1, k2, k3, whatever the value, right? So this is the one approach. The next approach, you see that there is a similarity transformation approach. In similarity transformation approach, what you have seen is that you need to find out a similarity matrix. Okay, you need to find out a similarity matrix. Let's say the matrix is P. How do you find out the similarity matrix? You, for that case, you need to find out the system should be controllable. Okay, because you have a controllable matrix, you find out the inverse of that matrix, because once, if the controllability matrix is singular, you cannot find it, right? So you find the controllability matrix, then take an inverse, and they take the last row, then take the last row as the first row of the p vector, p matrix. Let's say last row I'm commenting as a q. Okay, so p matrix contain q, qa, qa square in this way, right? And you get the similarity transformation matrix, and then do the similarity transform p inverse, you get some a bar, let's say, and similarly you get a b bar and c bar, and from that you find out you do the same approach, that same comparing approach. You find out the value of k, and then using similarity matrix you get the k, let's say k tilde, you get the k tilde, and then you have to find out the k for the original system. So why we basically interested doing this kind of thing, because it is when we do the simulated transformation, we basically simplify the system matrix, and with the simplified system matrix, it is very easier to find out the key. Okay, so sometime this place command is there, is basically the, how far I know, I'm not sure about all this, but it use this simulated transformation matrix. I hope, I'm not sure about all this. So if you try to, so my comment is not on that what place command is basically used, which procedure basically place command use. I am not going to say that. I'm saying that if you, let's say, this is the using this place command, you get this value of k. Okay. Now if you do it by your hand in your copy, definitely you use uh, that how you choose this p matrix depends on that, and based on that your system will you will get a different value of k. That's why what I'm trying to say is, but this is also correct, and if your calculation in copy pen, if you do the correct calculation, that is also correct. So my question is, you prefer, I would suggest you I would suggest that you should prefer this place command instead of this ACR command. Okay. Now you will see the in case of observer case. So I have this A and B. Let's say I have C. Okay. So first I start doing this with this A and this B. Okay. Oh, I do not need B. I need C. So C is, let's say, 1 and 0. Okay. So C is 1 and 0. And let's say your pole you want, as we have discussed in the previous class, that your observer pole should be 5 to 10 times further 5 to 10 times further in the length of complex frame from the controller pole. So you have controller use let's say -1 plus minus j. So I choose it -5 -7. Okay, this is P, and let's say L equals to less what is A transpose comma C transpose comma P transpose. So this is basically what you have done. Basically, you are finding out the control feedback control for the dual system, feedback control gain for the dual system. You basically try to find out the feedback control for the dual system. That is basically the origin system observer gain. Okay, and this dot define that element wise you are basically transposing. Okay, so you give A transpose, you give C transpose, you give P, and you get this. This is the L. This is the observer gain that you get. Similarly, you can use it for Ackerman using the Acker command. And for multiple case, you should use the place command. You should not use the Acker command. As in the last class, someone says that for multi-input play case, he basically he can use the Acker command for multi-input case, but this can't be done because once you do the multi-input case, your system, your B is no longer a vector, it becomes a matrix. Means it has a more than one column. So we cannot find out the inverse of a contributive matrix. So that's why you cannot use these things. But the loopholes of this simulate transformation approach or the Ackermann's formula is that they need a one strong condition, that is the systems to be controllable one. Okay, if the system is not controllable, let's say system is stabilizable, in that case you cannot use that. In that case, in the previous class we have already seen that you have to decompose the system into a controllable and uncontrollable format, like and if your uncontrollable modes are stable, then you only work with the controllable format and then find out the k value for that reduced system, convert it into the original system, and you will get the original value. This is the whole thing, and this is the all today. This is all about the today's class. Since no one is basically attending this class, so I am not able to take which question. What is your difficulties? So I just tried to find these are difficult. These are the things that we need to discuss. So I discussed it over here. So best of luck for your exam, and thank you for. I hope you can take this video. You can check this video from YouTube link, and we whatever the document that whatever I have written and showed to you in this class, I will upload it in the Google Drive that is shared with you. Thank you and best of luck. Thank you.